All right, let's go and review some things we talked about in our last couple of lessons. We began looking at a new way of doing proofs. So we've got two ways. One way is what we call the direct method of proof, where we make two columns of statements and reasons, and methodically we prove exactly what it says to prove. But then we started working on another method called the indirect method. Now that method has a couple other names, Brecken. Do you remember the other names for the indirect method? It could be called informal proof, or do you remember the other one? Yeah, proof by contradiction. There we go, proof by contradiction. And how does the indirect proof work, Michael?
It proves it by assuming the opposite. Proving the opposite. Yeah.
You got half of it, but if we stop there, we're in really bad water.
To assume the opposite of what you want to prove, and then prove that that is impossible.
There we go. So yeah, you start by assuming the opposite of what you want to prove, but if you stop there, then all we're doing is assuming something that's wrong. So then we want to prove that the assumption is absolutely impossible by arriving at a contradiction somewhere in the proof. And then yesterday, right at the end of the lesson, we began looking at statements where we take the hypothesis, that's the if, and we take the conclusion, which is the then, and we switch them. For instance, if two triangles have two sides and the included angle equal respectively, then they are congruent. True or false? If two triangles have two sides and the included angle equal respectively, then they are congruent. Is that true or false? That was our very first theorem, wasn't it? Our side angle side theorem. Well, if I flip the converse, if two triangles are congruent, then they have two sides and the included angle equal respectively. And we just switch the two. By the way, would that be true? If triangles are congruent, would two sides and the included angle be equal respectively, class? Yeah. In fact, everything else would be equal too. But yeah, at least those two sides and the included angle is equal. What do we call a statement that switches the if and the then, or interchanges the hypothesis and the conclusion? Abby, what do we call those? Cannot recall. Noah? Converse statement. Class, what's it called? Converse statement. As I showed at the end of the hour yesterday, is it always going to be true? If you take something that's true and you switch it, will the converse statement also always be true? Could it be true? It could be true, just not necessarily always true. Take your books out, open to page 63. Open to page 63, and let's look at some converse statements. Some converse statements. I do want you to note this, though. The converse of a definition will always be true. Because what is a definition? This equals that, correct? And so if you switch the sides of the equal sign, of course it's still going to be true, right? For instance, I don't know, think about a definition. If we define an angle as, an angle is two line segments drawn from a common point, okay? If it is an angle, then it is two line segments drawn from a common point. If you have two lines drawn from a common point, then it is an angle. You know, yeah, obviously that's going to be true. Look at number 3. Read number 3 for us nice and loud, if you would, Brandon.
Theorem 2 can be written as if a side and two adjacent angles of one triangle are equal respectively to a side and the two adjacent angles of the other, then the two triangles are congruent. Theorem 4 can be written as if the three sides of one triangle are equal respectively to the three sides of the other triangle, then the two triangles are congruent. State the converse of Theorem 2 and Theorem 4. Are they true?
All right, let's just start with the Theorem 2 part. So they've rewritten Theorem 2 for you. Do you see the word if? And do you see the word then? Okay, we're on page 63, number 3. That's what he just read for us. At the very beginning of number 3, it says Theorem 2 can be written as, and they write it out. Do you see the word if, class? A little bit later on, do you see the word then? At your seats, rework it. Just mentally, don't write it out. We're too lazy for that, but think about how would you restate it if you switch the if and the then. Take a moment to think, and when you think you've got it, Brandon, I want you to restate Theorem 2, switching the if and then, making a converse statement out of it.
Theorem 2 can be written as, if the two triangles are congruent, then a side and two adjacent angles of one triangle are equal respectively to a side and the two adjacent angles of the other.
Good. The only comment I'd make, did you hear what he said? If the two triangles are congruent, my only question would be the use of the word the at this point. The two triangles? What two triangles, right? So I say if two triangles are congruent, then a side and two adjacent angles of one triangle equal respectively to a side and two adjacent angles of the other. How many would think of the same thing he said? By the way, do y'all get what I mean by the words to the word the? It's called a definite article, so if you haven't specified something, it's hard to use the word the. Would that be true? If two triangles are congruent, then a side and the two adjacent angles of one are equal respectively to a side and two adjacent angles of the other. Is that true or not, class? True. Yeah, that would be true, CPCTE. Look at number 4. If the three sides of one triangle are equal respectively, then the two triangles are congruent. How would we restate that one? Dylan?
If two triangles are congruent, then the three sides of one triangle are equal respectively to the three sides of the other triangle.
Yeah. Is that going to be true, class? Yeah. And well stated as well. How many kind of seeing what I mean by switch the if and the then? All right, so here's the fun part. Now you get to write some out. So maybe have a little sheet of paper out with you. Scratch paper, it's fine. I don't really care. Maybe the back side of the quiz I passed back to you a moment ago. You could use that. But I want you to rewrite the converses of the A through G in that second column. Now, they don't necessarily always use the words if and then. So you're going to have to think through how to make an if and a then. For instance, on letter A, if you have an acute angle, then it is an angle less than a right angle. You kind of see how I made up some extra ifs and thens in there? That will make it easier. So imagine where the ifs and thens would go and then switch. I want you to do A through G. They're on page 63. And then think through the converse that you've written. Is it true?
Can you add you in there?
You can add in words as long as you don't change the meaning. But I would recommend figuring out how to work an if and a then into the mix. Times like this, you're thankful for shorthand. Just another minute or so to work on these. I know you haven't finished all of them yet, but you've had a chance to look some over, think some through, write some down. Let's do the rest of it mentally now. Letter A, an acute angle is an angle less than a right angle. How could we write that as a converse? Lana?
A right angle is an angle bigger than an acute angle.
Well, okay, so you tried to rework the entire wording. So listen as I say this. If an angle is acute, then it is an angle less than a right angle. If an angle is acute, then it is an angle less than a right angle. The switch would be, what do you think, Josh?
If an angle is less than a right angle, then you have an acute.
If an angle is less than a right angle, then you have an acute angle. Or then it is an acute angle, something like that. Does that make sense on the switching the if and the then? All right? By the way, would that be true, class? If an angle is less than a right angle, then it is an acute angle. Is that true or false? True. Notice that's a definition, isn't it? So we said a definition always is true when you take the converse. That would be no exception. Look at letter B. Brecken. An obtuse angle is less than a straight angle. Or you could say, if an angle is obtuse, then it is less than a straight angle. What did you have for the converse? All right, what do you think though? Listen again. If an angle is obtuse, then it is less than a straight angle. By the way, class, is that true? If an angle is obtuse, it's less than a straight angle, okay? So what would be the converse? Is less than a straight angle. Good. If an angle is less than a straight angle, then it is an obtuse angle. How many had something like that? All right, would that be true, class? Ooh, only sometimes, right? If an angle is less than a straight angle, is it always obtuse? No. Right angles, acute angles. Wait a second. I thought I said the converse of a definition is always true. Thoughts? That's not the definition of an obtuse angle, is it? What's the definition of an obtuse angle, class? An angle that is
greater than a right angle.
Greater than a right angle, less than a straight angle, right? By leaving out that piece of the definition, they still had a true statement, but the converse now becomes false. Interesting. All right, letter C. This one's a lot easier because they actually put the words if and then. If two adjacent angles have their exterior sides lying in one straight line, then the two adjacent angles are supplementary. What is your converse? And that is true, right? That's something that was an informal statement that we talked about. Adam, how would we make a converse out of letter C? Well, take everything after the word then and put if in front of it, and take everything after the word if and put then in front of it, then tweak a little verbiage as needed.
If two acute angles are complementary, then
Well, that's letter D. I was working on letter C.
Sorry.
It's okay.
If two adjacent angles are supplementary, then their exterior sides lie on one straight line.
There we go. If two adjacent angles are supplementary, then they have their exterior sides lying in one straight line. How many had something like that for letter C? Is that true? If two adjacent angles are supplementary, then their exterior sides lie in a straight line. That is a true statement, right? How about letter D? If the sum of two acute angles is a right angle, then the two acute angles are complementary. Abby, what do you think on this one?
If two acute angles are complementary, then the sum is a right angle.
All right. What do we think, class? If two acute angles are complementary, then the sum is a right angle. True or false?
True.
Yeah, that's definition of complementary, isn't it? The sum is a right angle. So yeah, that converse is true. How about letter E? If two angles are right angles, then the two angles are equal. What would be the converse here? Dylan?
If two angles are equal, then the two angles are right.
If two angles are equal, then the two angles are right angles, or then the angles are right angles. Is that true or false, class? Sometimes, usually not, right? Just because angles are equal doesn't mean they're right angles. So there, again, that's not a definition, it's a fact. Right angles are equal, but just because they're equal doesn't make them right angles, does it? So, yeah, letter E, the converse would not be true. How about letter F? How would I make that a converse? If a triangle is isosceles, then the bisector of the vertex angle of the triangle is perpendicular to the base. How do I make that a converse? Come back to Lana now that you've heard a few of them.
If the bisector of the vertex angle of the triangle is perpendicular to the base, then the triangle is isosceles?
Good. The only change in word I would make is if the bisector of the vertex angle of a triangle is perpendicular to the base, then, and you did correct this, the triangle is isosceles. Ooh, would that be true? If the vertex angle bisector is perpendicular, would the triangle be isosceles? We bisect, and it's perpendicular. Does that make it isosceles?
Not all the time.
Angle, side, angle, they have to be congruent, don't they? So these have to be equal, don't they? So is it isosceles? That took a little bit more thought, but that converse is in fact true. How about letter G? Make a converse. If two triangles are congruent, my book says congruent.
Yeah, mine is.
Yeah, I missed the U, yeah. Anyway, took you out of it. All right, if two triangles are congruent, then the three angles of one are equal respectively to the three angles of the other. Again, is that true, class? Two triangles congruent, the angles are equal? All right, what would the converse be, Michael?
I think I might have. No, I didn't. If three angles of one triangle are equal respectively to the three angles of the other, then they are congruent.
Okay, if the three angles of one triangle, and notice he kind of had to rework a little there, are equal respectively to the three angles of another, then the two triangles are congruent. Would that be true, class? If these three angles equal those three angles, congruent triangles?
Sometimes.
No.
Yeah, we actually did this, didn't we, not that long ago, where we had equal angles here, equal angles here. Obviously, that means these angles have to be equal. We haven't proven that yet, but it's kind of, are they congruent?
No.
Now, you got to have at least some side in there to make sure they're the same length. So, again, it's a true statement by CPCTE, but then the converse is not true. Again, well stated, but just not true. All right, so just something to think about as we talk about different things, because as we go from theorem to theorem proving things, we will occasionally come across converses, and there's the thought in the back of your mind, well, we already proved this. Do we really have to prove that? I mean, it's just the converse. Do we have to prove it, class? Yes. The only thing we don't have to prove are definition converses. So anyway, turn over to page 64. Flip over a page, if you would. And I've got some little tips here. So a little bit of information on the page that may kind of guide you as you begin doing more and more of each proof on your own. Go ahead and read that first little box there. Prove a pair of lines equal, Josh.
Show that they are corresponding lines in two congruent triangles, and show that they are sides opposite equal angles in the C.
Y'all see what they're talking about there? If we want a couple lines equal, method number one, congruent triangle CPCTE. Or, if the two lines are in the same triangle, if you got their opposite angles equal, the lines would have to be equal, right? So now, our analysis becomes, oh, I want to prove two lines equal? Are they in the same triangle, or are they in different triangles? Same triangle, if the opposite angles equal. Different triangles, let's get them congruent CPCTE. Similar note to prove a pair of angles equal, Noah.
Show that they are corresponding angles in two congruent triangles, and show that they are opposite equal sides in the same triangle.
See what we're talking, same kind of thing. Are the angles in different triangles? Get them congruent CPCTE. Are the angles in the same triangle? Okay, then get the opposite sides equal, and then you got the angles equal. Says here, in working out exercises, it's very desirable that you acquire a definite method of attack so that when an exercise is assigned, you have some system to your procedure. You're not just randomly guessing, I don't know, this line equals itself by identity. That angle kind of looks like a right. I don't even know. Okay, we don't want to go willy-nilly. You know, it's like Frank Reich. Colts have to play a week 1 game? That's the worst team in the NFL. What are we going to do? I don't know. Just go out there and play ball, boys. I mean, I don't know. And then we stink against the Texans. He's like, well, that was bad. What should we do next week? Well, let's try the same thing against the Jaguars. We got shut out. Oh, maybe we should come up with a plan. Sorry, just venting. Anyway, there is no specific method that can be used to solve all exercises in geometry. And every other offense needs a different style of defense. Every opposing defense needs a different offense. Every proof's different. Do them all different. However, some general suggestions may be given to tell you how to start and thus give direction to your efforts. Read step number 1 as we look at doing proofs. Abby?
Draw carefully, figure representing what is given.
There's more.
Oh, I didn't see that. The figures should be as general as possible.
She's like, parentheses. I learned in English class that those minimize. That must be worthless. My eyes will just bleep that right off the page. Yeah. Okay, so draw a picture. Now, right now, your sketches are given to you, and this whole quarter, the sketches will be given to you. Okay? This quarter, second quarter. My brain just put us in the second quarter. We're not there yet. Second quarter, the sketches will be given to you, but as the quarter wears on, I'll start coaching you into how to come up with your own sketches. As we get into the third quarter, you'll start providing your own picture, but by then you'll have learned how to do it. Notice though, it says everything should be as general as possible. Don't make something look perpendicular if it's not. Don't make things look equal if they're not. Don't make a triangle look isosceles if they don't tell you that it is. So try to keep things as general as possible. Number 2, Adam.
Determining specifically what is to be proved usually reduces to proving a pair of lines or a pair of angles equal.
Yeah, figure out, okay, they say they want me to prove this, but I could prove this if I got this, and I could prove this if I got that. How do I get that? And that's usually where the crux of a proof. Usually it all hinges on if I could only get these 2 lines equal, or if I could only get these couple of angles equal. That's really what a lot of proofs boil down to. So in other words, do your analysis, do your thinking. What is it going to take to finish the proof? Number 3 is kind of duh, so Brecken.
Recall the various ways you have had for proving this.
In other words, think back. How have I proved this in the past? One of the benefits, if you've been keeping your proofs, maybe in a pocket of the notebook or something, is you have something to look back on. Or at least you have a notebook with, let me flip through my theorems and corollaries. Remember the other day, we were doing the Theorem 5 proof, remember? And I said, whoa, something's bigger than something else? We haven't done a lot of this. And I made you look through the notebook to find that only 3 times we'd had anything about unequal anything, right? That's kind of what number 3 is if you need to, do some research. Look back in your notebook. It's your entire set of legal precedent, so to speak. Dig through there, find what we've done in the past, or find statements we know, and when you find something useful, apply it to the proof. Number 4, go ahead and read that, Josh.
Determine which of these ways is the best for the case at hand. This may be done by elimination if it is not evident at once.
All right, and this is kind of where we've been to, right? I've said, okay, we got these 2 triangles. How do we prove them congruent? What are my ways to prove congruent triangles, class? And we'll list out the ways, right? And that's kind of, okay, these are all the ways I have to prove it. Now, which one's the best way? Well, what do we already have? Well, I got a couple sides, and I got a couple angles. Well, I know side probably ain't it. If I got angles, I probably want to use them, right? And so we kind of process of elimination, figure out the best way. Kind of along with number 4, I just kind of referenced it, but number 5, Lana?
Determine what parts you have and what parts, if any, you want to use this method.
So for instance, if I want to do side angle side, I say, well, I got a couple sides, so what do we need? Angles! Okay, let's figure out how to get the angles. Number 6, again, kind of duh, but read it for us there, Brandon.
Determine how you may get the parts that are lacking, either by a
reapplication
of the above steps or by some construction line.
Yeah, in some cases, we need an auxiliary line, right? That's kind of what we came to in the Theorem 5 proof is, well, if I can prove this is a part of that, well, maybe we can make it a part of it by drawing an auxiliary line and getting something like that. And then number 7 is not something you will have to do, but we will do as a class from time to time. In fact, we've done it a couple times already, Michael.
When the direct method of proof is not apparent, try the indirect method of proof.
There we go. All right, so that's just kind of some guidelines to kind of a general strategy here. Let's take a look at number 2 here on page 65. And if you would, go ahead and on a sheet of paper, copy down this picture. Kind of an interesting looking picture. We've got this angle kind of open backwards of what we're used to. And we've got this angle A, and there's a point B. And whatever the length of AB is marked off here at C, so that, as you can see from the picture, AB and AC are equal. And then this AB line is extended out to an E, and the AC line is extended out to D. And then we've got a couple of, it says, angle bisectors. Bisecting the exterior angle at B, and bisecting the exterior angle at C, and these 2 bisectors intersect at O. So then copy that picture on your paper. I'm going to number these these angles 1, 2, 3, 4, 5, 6. So I'm going to number the angles here to make my life a little bit easier. And then we'll copy down our given. We're given equal lengths AB and AC, and we're given that OB and OC bisect angle EBC and angle DCB respectively. And of course, underneath that, copy what they want us to prove, and that is that the two bisectors themselves, the lines OB and OC, are equal. Once you got that down, 2 columns: statements, reasons. Once you got that down, 2 columns: statements, reasons. Of course, get down your first statement and your first reason. Once you got this copied down, put your pencil down so I know that you're ready. And then as needed, kind of look up this way, but look at the proof and start thinking if you can figure out maybe a plan of attack. While you're waiting for your classmates to finish copying, you be thinking, how could we make this happen? All right. Now, before I put my strategy together, I want to take care of any clang that I see. And I do see a couple of clang phrases here. What's one clang that you see? Dylan?
Bisect.
I see bisect. All right. So at your seats, we got a bisector. Go and get down statement 2, and let's clang off of the bisect. What do we write for statement number 2, since OB and OC bisect angles EBC and DCB respectively? Brecken? If OB is a bisector, what does that mean? Okay, so what are they? The bisector's right here. OB bisects angle EBC. That angle is bisected. That's the line that does it. Okay, so what should I write for statement 2? There we go. But it's not that OB is the only bisector, right? I've also got OC. That's also a bisector of angle DCB. So what else could I state in number 2 bracket? Angle 4 equals angle 5. And what's the reason here, Dylan?
Definition of angle bisector.
Definition of angle bisector. How many thinking the same thing Brecken said? There's another clang thing here in the given. And Brandon, what did you notice?
AB equals AC.
All right. What's so clang about AB and AC being equal to each other, Lana? How is that clang that AB and AC are equal?
How's it clang?
Yeah. I mean, 2 lines equal is a Clang statement?
Would it be side angle side?
What do we use side angle side for?
Congruent triangle.
Congruent triangles. I don't have anything about congruent triangles, but at 2 lines equal, maybe an AC.
I don't remember.
Noah, help?
I always get stuck on that reason.
Angle 6 equal angle 3.
I'm sorry?
Angle 6 equals angle 3.
Okay, in a triangle, and it looks kind of funny, but that is a triangle, isn't it? I've got 2 equal sides. AB and AC aren't just random equal lines. It's not like AB's right here and AC's over there. They're just separate, unrelated lines. They're connected into the same triangle. And class, if in a triangle 2 sides are equal, the opposite angles are equal. So yeah, number 3, Noah, you said state what?
Angle 3 equals angle 6.
Angle 3 equals angle 6. And what is that reason there, Lana?
Because the angles opposite the equal sides are equal.
Angles opposite equal sides in a triangle, so we'll add in those words, are equal. Angles opposite equal sides in a triangle are equal. I got a whole bunch of equal angles now, don't I?
Yeah. I don't remember.
All right. Let's zoom in just a bit more so it makes it a little easier to see here on the screen.
It's a weird picture.
It is, yeah. Any more clanginess? Any more clangage?
No.
Yeah, I didn't think so either. Okay, well, let's look at what we're trying to prove. I'm trying to prove OB and OC are equal. Now, OB is right here, and OC is right there. Thoughts on those 2 lines? Because I want to prove a couple of lines equal, right? We just read this in a box right across the page. How do I prove lines equal? Adam? Right across the page, there's a little box that says how to prove lines equal. How do I get lines equal, Adam?
Show that they are corresponding lines in 2 congruent triangles.
Okay, or?
Show that they are sides opposite equal angles in the same triangle.
All right, so it says if these 2 lines happen to be corresponding parts of 2 congruent triangles, then I can get them equal. What 2 triangles are these lines in, class?
None.
They're not in 2 triangles, are they? They're in the same triangle. So do you see that in this case, well, I mean, unless maybe I drew a little line like that or something, right? Maybe then I could make 2 triangles. Or the other option, Adam, was if they were in the same triangle.
That the sides opposite equal angles in the same triangle.
Show that they're opposite equal angles in the same triangle. Well, OB and OC are in the same triangle, are they not? What angles are they across from, class?
3 and 6. Or
They're across from 2. OC is directly across from 2. And OB is directly across from 5, correct? Within this triangle.
2.
They're directly across from 2 and 5. Does everyone realize that if angle 2 and angle 5 were equal, OB and OC would have to be equal? Does that make sense? So really what the proof comes down to is, I need that right there. If I can get 2 and 5 equal, I've got my proof. Thoughts on how to get 2 and 5 equal? Michael?
Angle C is equal to angle 4 plus angle 5 plus angle 6, and then angle B is equal to angle 1 plus angle 2 plus angle 3.
Okay, that's true. Angle B is the whole 1 plus 2 plus 3, and C is the whole 4 plus 5 plus 6. Michael, where are you going with that next?
That 3-step thing with substitution and subtraction.
Oh, okay. I see where you're going with this. All right, so Michael's thinking if angle B were equal to angle C, which would be equal to C, bracket? Would this angle at B be equal to this angle at C? Yeah, and again, it doesn't say it is, but it said for our purposes, if something appears to be a straight line, we'll give it the benefit of the doubt. Probably geometry purist would say you should have stated that EBA is one continuous straight line, or AE is a straight line. But yeah, we do have straight angles, and we know in class that all straight angles are equal. Though we could get a little quicker here, if instead of stating that they're equal to the straight angle that way, we could say B is a point, and if we're going to say that EA is one straight line, the sum of all the angles about a point on one side of a straight line equals a straight angle. I think it's in formal statement 10. Let's use that. Let's say that angle 1 plus angle 2 plus angle 3 equals a straight angle, and angle 4 plus angle 5 plus angle 6 equals a straight angle, because the sum of all the angles about a point on one side of a straight line equals a straight angle. Where we're making the assumption that AE and AD are indeed straight lines as they appear to be. Now, the way I described the drawing to you, I said draw two lines and then mark off a distance B on one, mark off the same distance C on the other. So in my verbal description, we did state they were straight lines. So therefore, 1 plus 2 plus 3 is a straight angle, 4 plus 5 plus 6, that's a straight angle. And then, Michael, you were going to say...
I blanked.
Well, we've got these three add up to a straight angle, and those three also add up to a straight angle.
Angle C is equal to angle B.
Or we could just say that 1 plus 2 plus 3,
Equals 4 plus 5 plus 6.
because they both equal straight angles. Because anyone? All straight angles are equal. You could maybe argue a substitution or a quantity is equal to the same quantity or equal to each other. I think the more comprehensible way of explaining it is that all straight angles are equal. And since we already know, and this is where Michael's going next, right, that angle...
C equals angle B. What? I'm trying to copy everything down.
Oh, okay.
Well,
All right, somebody else kind of take over here. See, Brandon Dillon, you've helped me already. Michael's helped me. Brecken, yeah, he helped me. Abby, way back in the corner.
Well, you could do the subtraction axiom.
Okay, what would we subtract? Good, we can subtract away angle 3 and angle 6 because they're equal and they're on opposite sides of the equal sign. So if we subtracted them, Abby, we'd be left with...
Angle 1 plus angle 2 plus angle 4 plus angle 4.
And that's simply the subtraction axiom. Now notice how close we are to getting angle 2 and angle 5 equal. The only problem is, what would I have to do to get 2 and 5 by themselves, class? Subtract away 1 and 4. Do I know that 1 and 4 are equal?
They are.
How do we know? Yeah, Joe Biden's going to solve all the world's problems. I just know. I'm going to vote for him. You laugh, but supposedly 80 million people did. With about as much reason as Lana just... Oh, sorry. Getting off politics.
Not if
All
they're
right. All right. They just knew they hated Donald Trump. That's really what it was. All right. Got a couple hands there. Noah? Okay. If we get, say that louder. If we get EBC right here and DCB here equal. So EBC, you mean 1 and 2? If we could get that equal to DCB, you mean 4 and 5, then angle 5 and angle 2 would be equal because he's right there. He really is. So everything's right. You haven't said anything wrong yet. I'm just trying to get to the end. Well, let's take what we've got so far. Okay, I've got some hands, but let's take this. I do know that 1 plus 2 is EBC, right? But we need to state that it is. So let's go and say that 1 plus 2 is EBC. And, well, you know what? No. I like something better. I like something better here. I think it'll be quicker. Not that your method is wrong, but we may have a quicker way. I don't really care about the 1 and the 4, do I, class? But I do like the 2 and the 5. I don't like the 1. I like 2 better. Thoughts? Now, it was kind of weird looking, but what would I get if I substituted here? Right? And that's substitution. I'm curious if this is going to be fewer steps or not. I don't know. And if I have an angle 2 plus another angle 2, what do I have, class? 2 angle 2s, right? So we could say that 2 angle 2s equals, and I've also got 2 angle 5s. That's just algebra, I guess we could say. I mean, counting, I don't know, algebra. And then what could I do to get the 2 and the 5 equal now? How do I cancel them away? I divide both sides by 2, right? Dividing equal quantities by the equal quantity of 2. So number 9, angle 2 does equal angle 5 because a division axiom. If equals are divided by equals, the quotients are equal. And we said it's what we really wanted, right? 2 to equal 5, but why was it we wanted 2 to equal 5 again? There we go. In a triangle, the sides, OB and OC, opposite equal angles, 2 and 5 in a triangle are equal. So number 10, yes, OB does equal OC because in a triangle, sides opposite equal angles are equal. Now the question is that faster than what we would have done the other way? I don't know. Here was my thought. Here's a strategy tip I want to give you. I'm not sure how much time it would have saved on this particular proof. But when we say that angle 1 and angle 2 are equal, they are how much of the whole angle, class? As we kind of just showed here. They're halves. So here's a strategy tip. If you get one thing bisected, 2 equal parts. If you have 2 things bisected, you may want to write this somewhere in class notes, or maybe write it at the top of this paper and go ahead and put it in your class notes. If you have 2 things bisected, state that you have equal halves, because that could have possibly saved us some trouble. If I'd said right here, I'm going to write it in white, angle 1 and angle 2 are equal halves of angle EBC. Angle 4 and angle 5 are equal halves of angle DCB. That's still the definition of an angle bisector because we did specify in the definition each part is half of the whole. And we said that they're equal. This kind of takes the full scope of the definition. They're equal halves. Because then right here I could have said angle EBC, and angle 3 is a straight angle. Angle DCB, and angle 6 is a straight angle. Isn't that true? DCB plus angle 6 is a straight angle, isn't it? EBC plus angle 3 is a straight angle, isn't it? And so we would have had that angle EBC and angle 3 equals angle DCB and angle 6. And so when we subtract away the 6 and the 3, there's my EBC and DCB. Halves of the equals are equal to each other. I think we could have done it in a couple fewer steps had we taken that approach. Nothing wrong with the way we did it. Kind of reinforced the idea of bisector being halves. But it's a strategy tip moving forward. 2 things bisected, state that you have equal halves. It'll save you a little bit of time. 1 thing bisected, the halves probably don't matter. But 2 things bisected, you might want to get the halves equal. Because since 1, 2, 4, and 5 are all halves and equals, all 4 angles are equal to each other, aren't they? But that wasn't something we could have said the other way. Adam, you had your hand up. No question?
No.
All right. Questions on this? Questions on this? All right. For homework this evening, I want you to do handout number 11. Handout number 11. Just a reminder, we have our exam coming up in lesson 43. Notebooks we'll be doing lesson 43. That's Friday for you guys. On Monday, I'll be giving you your check sheet, and Gavin, I will be giving you a check sheet as well. I'll email it to you. And so you can make sure everything's in the notebook there. I'll give you some more instructions there. Handout number 11 for Gavin. For the rest of you, it's the handout you're getting right now. And you're going to see that equal halves on the handout tonight. Let's get a little bit of practice with that equal halves thing. All right, handout 11. 7-step proof. I've given you 3 statements. You fill in the other statements and all the reasons. We'll take a look at it in our next lesson. All right, when the bell rings, you'll be dismissed. Have a wonderful rest of your day.